Okay, in this example, I want to work through an acid-base titration, specifically the titration of a weak acid, nitrous acid, with a strong base, potassium hydroxide. Okay? Now, the first thing I've got to realize about this titration being a weak acid, strong base, is that the equivalence point pH is going to be above 7. Okay? So when I do my calculation for the equivalence point pH, I should get an answer somewhere above 7. So here's the reaction that's taking place. The nitrous acid is neutralized with potassium hydroxide to create water, and the salt would be potassium nitrite, but potassium is just a spectator here, so I'm not too worried about it. Now, equilibrium will be established on this. Okay, so the first thing I've got to realize is equivalence point means that you have equivalent moles of acid and base. Okay, I'm given the molarity of my nitrous acid and the volume of nitrous acid used. I can solve for moles of nitrous acid, 0.004. Now, these two, the weak acid, strong base, are reacting in a 1-to-1 ratio. So the moles of nitrous acid will be equal to the moles of potassium hydroxide needed, because I'm getting one hydrogen, one OH from each species to create that water, do the neutralization. So I'm going to take then the moles of nitrous acid, 1-to-1 ratio means I would have that many moles of OH. The molarity of the potassium hydroxide, I can solve for unknown liters of potassium hydroxide needed. I solve, get 0.02 liters or 20 milliliters of potassium hydroxide needed. So I'll have my 40 milliliters of weak acid mixed with 20 milliliters of my strong base to reach my equivalence point. Now, that gives me a total volume of 60 milliliters in the beaker or Erlenmeyer flask. What is the pH at that equivalence point? Again, I can predict that it will be greater than 7 because I have a weak acid with a strong base. The weak acid will form an equilibrium, so it will come back. So I'm going to have some OH there that will push the pH above 7. So what I want to do here is I want to get my Ka value for the nitrous acid. This comes from a reference table in your chemistry book, 4.6 times 10 to the negative 4 at 25 Celsius. I know my pH is going to be above 7, so I'm going to derive the Kb value from Kw divided by Ka. Remember that Kw is 1.0 times 10 to the negative 4 at 25 degrees Celsius. Divided by our Ka value gives me a Kb of 2.2 times 10 to the negative 11. I write an equilibrium expression in regards or in respect to the Kb. Here is that expression. Okay. So nitrous acid, hydroxide ion, and the nitrite ion. Okay. Now, this Kb is extremely small, 10 to the negative 11th, in comparison to my molarities that are both at 10 to the negative 1. So I'm going to make the approximation, the 5% approximation that you're familiar with. I'm going to say that the change in the concentration is very small. So I don't necessarily have to set up an ice table. I can just then define X and X over the molarity of the NO2 negative, okay, which is the conjugate base of nitrous acid. Okay. Now the molarity of this is not the 0.1 or the 0.2 of these original solutions. We have the moles, 0.04, okay, from here, okay, but the volume is not the 40 milliliters or the 20 milliliters. It is the total volume. Those two have been mixed together in the same container. So it is 60 milliliters, which is 0.0600 liters. And so that is my molarity at the equivalence point. So I then solve. So Kb, 2.2 times 10 to the negative 11, multiplied by the molarity, yields x squared. Take the square root, and I get x to be equal to 1.20 times 10 to the negative 6, which is representative of that hydroxide ion concentration that I would see present at the equivalence point. I'm going to do a POH, since this represents the hydroxide. Negative log of hydroxide concentration gives me a POH of 5.92. Subtract from 14, 8.08 is the new pH value at the equivalence point.